working on researching that. And then before we go into the detail, just some regular announcements. We have another invited speaker meeting coming up. Also, that note the time is a little bit different from what we are regular timing. These two kind of had to change a little bit. So sorry about that changes. That might confuse some folks. The next one will be on the 16th floor, our regular meetup room. So please make a note of that. And then we are also trying to work on another December 1st or 2nd week, more of an AI panel discussion. We did, I think, last year sometime. It was a good response. So I'm trying to see if we can get some good speaker to work with. But stay tuned for that. We'll be doing it in the IBM Client Center location, so if that helps for some folks. With that, planning for 2020, of course, we can help if you want to do sponsorship. That helps our group. And then we have Capital Factory dates. They're our regular venue sponsor. We're also thinking of some AI job event or something of that sort. It's still everything on the planning phase. And also we're planning to do some live broadcasting apart from the Capital Factory. So those are the cool things coming. Stay tuned. For today, we have our sponsor, Spark Cognition, our very generous regular sponsor. Give a big clap of hand and welcome them. Thank you. And yes, and the Capital Factory, our venue, and we would like to get some lightning talk session where anyone with any work item, like 5-10 minutes, if you're working on, you're struggling to get something set up, anything, just anything that related to AI, machine learning. If you want to present, you can have some opportunity. Get in touch with me after that, then we can work on it. We do have basically set up a non-profit organization to drive this, so it helps us going with reaching out to different speakers and different venues, set up all this stuff. So that's our non-profit is AI for Greater Good. It's a Texas bed. We just got our 501c approved federally, so that's a good thing. So with that, we come to our today's speaker, Elad, I think, Liebman, senior data scientist in Spark Cognition, and he'll give us cool talks about what he's working on. Just a little bit background, I think he's working on online adaptation, autonomous decision making. Maybe you can elaborate on what that is and a little bit in depth. And he's been active in UT Austin Standard Perform League and a lot of cool stuff. So with that, I'll invite Leb. Please come. And
thank you very much for
thank you.
warm introduction. As I'm getting connected, I'm not sure I'll need a mic. As I'm getting connected, I'll point out that these are Tito's handmade vodka cups to be drinking water with, which doesn't look rather suspicious. So allow me to assure you that this is water. Where would you want me to put it? Just in the machine? Okay, perfect. No problem. Okay, perfect. So, thank you very much for coming, and let me just connect real quick. So, as I described, I do work on autonomous decision-making at Spark Cognition, but I would like to, in this talk, discuss at length applications of autonomous decision making to a, I would like to say, more, a more off the beaten path domain, which is music. And this is one of the things I've worked on in my PhD dissertation and after. And without further ado, we'll begin. So we are witnessing, we're witnessing an explosion in artificial intelligence research where more and more artificial intelligence applications and tools permeate our immediate surroundings, from our cars and our thermostats and our phones. But if we want to develop artificial intelligence that is able to interact with people on a daily basis, AI needs to be able to understand the human cultural experience. It manifests itself in many, not necessarily obvious ways. Now, it's easy to think about, navigation recommendations, but it becomes trickier when you think about more subjective things like music or film. Now, I want to give you like an example that people don't necessarily think about very often, which is song transitions. Just out of curiosity, how many of you have ever made like a mixtape, like a mix CD for friends? Okay, so there's always quite a few people who've done this. Now, the audio is supposed to work, but supposed to is a pair of words that I always dread, so let's see if this works. Now, I'm going to play a couple of transitions to you, and we're going to do like a show of hands of which one you liked. Okay, so let's start with one. It's working. Okay, that was one. How many of you like this one? Like you thought it was a good transition? Okay. How many of you thought it wasn't a good transition? Okay. So, how many of you liked the first transition more than the second transition? Okay, how many of you liked the second transition more than the first transition? Okay, so I see hands went up and down every question that I asked. Typically, this is not the first rodeo. I've asked this with different mixes, but I've asked this type of question to different audiences. And what has happened is that typically about a quarter to a third like one more than the other, and about a quarter to a third like the other way around, and the other part just doesn't care or doesn't understand what I want of them at all. And that's typically how this works. And the overall compound picture that arises is that this is actually a difficult question to ask people. And even more difficult to reason about with computational means. Because it deals with aesthetics, and it's inherently subjective, and preferences are elusive. Like, people know what they like, but if I asked you, what do you like? And you were at one of my talks before, I remember you were in. I think we talked about Sly and the Family Stone. Okay. And if you ask people, what do you like? Explain to me what you like. Not a lot of people will be able to necessarily talk cogently, explain in technical terms that people would understand what it is that they like. And music in itself is just very, very complicated. It has very loose semantics, and it has many aspects. Like, you can parse it in many different ways, and you can conceive of it in many different granularities and resolutions. So to teach computers to reason at that level about like sequencing songs in a way that means something to people is a very difficult question. Which is why I'm trying to basically establish this as a worthy pursuit for artificial intelligence research. If you're not bought on the premise at this point, you might as well just leave. So, okay. Where's my notes? Okay. Okay. I'm going to talk a bit about music playlist recommendation, and specifically about a project that I've been involved with. And this work has been published in multiple venues, in like a couple of science conferences and the MIS Quarterly this year. And the core idea is that if you think about music streaming services, that by and large invested a lot of resources in trying to figure out which songs certain people would like. But they haven't spent a lot of energy necessarily, or at least it hasn't been exposed to us, how they conceive of sequences of songs, and not just in single song preferences. But the reality of it is that people don't just listen to one song and then go about their business. People listen to music in sequence, multiple songs at a time. So how do you factor that into the construction of a music recommendation system? So the key insight here is that you actually want to not just model individual song preferences, but also model transition preferences, which can also be captured by a computational model. And for that purpose, we use a framework called reinforcement learning. So just before I dive into it, reinforcement learning is a paradigm of machine learning that rather than just focus on, the classic example of supervised learning, where I give you examples and I give you annotations, and you teach a model to try and predict unannotated examples based on the annotated examples, or unsupervised learning, when I just give you a bunch of examples and I expect the learning model to recover some sort of structure. Here you're basically training a computational model to interact with an environment. The environment gives you a signal, you perceive the signal, you make some decision, you send the decision back to the environment, you get back feedback, and then you update your model, and this continues. So this type of reasoning, interactive reasoning with an environment, is best captured by a mathematical framework called Markov decision processes, which is, I don't want to dive too deeply into the nomenclature, but the idea is that you have some mathematical entities that capture your state in the world, some mathematical entities in the model that basically capture the transition dynamics, like if I am in state S and I take action A, my world state changes to state S prime. Like if I am at state S now and I take a step forward, I am now at a new state. Now, in this case, there's questions about stochasticity. Like, if I took a step here, is this deterministic? Now, it depends on how you look at it. If the world is divided roughly to like a grid, you can say that it's roughly deterministic. Like if I go take a lateral step, I get to the adjacent cell. If you're a robot and you're actually reasoning in an actual physical space, then there's ambiguity as to whether I'm actually here or 2 centimeters to each side, so a half an inch to some direction. So it really, really depends on how you're representing the reality that you interact with. In a discrete action and state space, like where you have discrete number of states and discrete types of actions, it's basically a graph that you traverse, that each decision takes you with some probability to a different edge. Okay, now, what is the Markov decision process of music listening, music recommendation? You can basically say, in the most abstract sense, that the things you've listened to in an immediate context are your state, or at least the visible state. I'm not going to dive into that nuance necessarily. Your action space is all the songs the agent can recommend to a listener, the entire corpus. You pick a song, you play it, that's the next song. Your next action is the next song, you play it to a listener, you get some signal of reward. What is that reward? We're going to talk about that later. And then you move on to the next step, which is basically the next sequence in the chain of song recommendations. You can visually think of this as kind of like a traversal in song space. You're just moving between songs over time. Okay. You can do all this with formal language. I'm going to skip this slide with your permission. Unless anybody, if anybody wants to go back to it, it's slide 8. Just tell me slide 8, we'll go back to it. Okay. If I now actually want to build a music recommendation system, I need some data that basically describes song to me. So, fortunately, there are archives. One of them, the most commonly used these days, is called the Million Song Datasets. It has close to full analog descriptors for the full recording of the data for a million songs, as the name implies. It has a million songs, and almost about on the order of like 45,000 artists. You can use that, that raw information, audio information, or you can construct some sort of shorthand representation for the songs. In this specific project, we focused on capturing information relevant to timbre, like the spectrum of the audio over time, rhythm over time, pitch, and loudness, like how different amplitudes at different ranges of the spectrum. And all in all, you get this neat compressed representation, 34-dimensional representation for each song in the archive. Okay. Now, that in itself, the framework is completely robust and generic, and you should separate the specific implementation details that we used for practical purposes with the framework itself, which is tunable. But for this purpose, you basically take all the features, partition them into bins, and then you can say represent a song, but the quantile representations of its feature for each feature. The nice thing about this kind of discretized representation, it also gives you a kind of natural representation for transitions. Because you basically say, if I move from song 1 to song, you go from feature, from the third quantile of feature X to the fifth quantile of feature X. And I can do this for all the features. So I have this clean, discretized representation for transition dynamics as well. So, now we go back to the big question, which is what is the reward function here? The reward, the agent, if you think about in reinforcement learning terms, the goal of the agent is to interact with the environment in a way that maximizes reward. And what does maximize the reward means? Whatever you define it to mean. In this context, you want to maximize listener enjoyment. And I'm going to get into where you get this raw listener enjoyment signal. But let's assume that we have that signal. You need to figure out how to represent it mathematically so you can learn how to predict it. So we're making a bunch of simplifying assumptions. One of them is that you can basically decouple the transition, the component from the song component. Like there's an aspect of the reward which is how much you just like the song, and there's an aspect of the reward which is how much you like the transition. And you assume that they're linearly inseparable. Now we know this isn't true. We know that one affects the other, and we're actually going to show in the empirical analysis that we see how that actually happens. But we need to start from somewhere. So we do that. That's one thing. And the second thing that we make an assumption is that basically you can model the entire transition as a decaying weighted sum of individual per feature transitions over features and over songs. So I don't want to dive into the specifics of how this reward function is constructed. It's kind of similar to tile coding, if anybody is familiar with the concept of tile coding from reinforcement learning. It's the idea that you can take the same state space, partition it in different ways, and then represent the reward as a sum of weighted partitions. So you basically learn a kind of a linearized representation, a linear approximation of the representation. So it's basically what we're doing, only with song transition and preferences. But we get basically, we assume that the whole thing can be represented as a roughly 4,000 weighted coefficients. It's still a lot, with all the simplification that we made. And the idea is that as you go back in time in your playlist, older songs matter less and less to the next transition. Now, this is the full learning architecture of this music recommendation agent. You have a song corpus M and a sum target length K. You start by initial exploration where you basically learn song and transition preferences. You have to start with some, this way, basically you play different songs This is not done actually randomly. It's actually done in a way that samples the song and its transition space as intelligently as possible under the time constraint. Gets some rough approximation. Uses it to try to predict possible song subsequences. Pick the next song that leads to the most promising subsequence. You send it, you get some signal whether the user liked it or didn't. You update your model, and this continues as long as the playlist continues. Now, how does this actually work with human listeners? Human listeners, it sounds like what's the alternative to human listeners? But you do so much stuff, like, because we tested this on dogs, on chinchillas, it works great. No, we tested this with simulations and then with a lab with human participants. I'm sparing you the simulation results because the proof of the pudding is in the eating. That's assuming that actual people eat it. So we tested this in a lab with 47 helpless participants, undergraduates, and basically what we're looking at is, I'm used to standing by the board and presenting, and I'll just try and describe it. The top row is a histogram of preferences, frequency, in initial training mode. So the farther you are to the right, the more likes a person clicked during listening. So it means that you like the playlist more. Now the whole playlist is 25, so the max could have been 25. As you can see, most of the time you're not getting that many. People are not that generous with their likes. So you started off with about 12 and a half, 13, and about 10 for transitions. Now, after it's learned, and you actually deploy it, you keep learning, but you deploy the learning algorithm, we compare two variants. One actually tries to also predict sequence and try to optimize for sequence. And the other one is more vanilla recommendation system, just tries to maximize over songs, regardless of order. What is interesting to see is that we see a demonstrable improvement in likes over songs for both the transition-aware and the transition-unaware variants. But if you look at the transition reward, like how many times people actually said they liked the transition, people like the transitions a lot more when you're actually actively modeling for the transition. Now, it's important to point out that people like the transitions a bit more even without being transition-aware. And that's because liking the songs increases the likelihood of liking the transition, so it's not, as I said, completely orthogonal. And also, it's quite possible that reducing, if you only recommend songs that you like, if there's going to be a higher likelihood of ending up on good transitions as well, just coincidentally, because they're not independent. But still, we can say that we actually improved dramatically liking the preference, the sequence as a whole, compared to just liking the songs without any preference to the order. Any questions? Any questions up to this point? Okay. Now, it's important to note that once you learn some model, that still doesn't mean you know how to necessarily use it. Especially if you're planning 10 songs ahead, 20 songs ahead. Being able to, given a model, produce the best playlist possible is still a hard problem. It's called a planning problem. It basically means that it's an oracle now that tells you, like, you give it a transition, it gives you a prediction of how much you'd like the transition. But now you can't exhaustively enumerate all possible transitions and let it pick the optimal one, because that's not computationally possible. Imagine you're playing for 10 songs and you have 10,000 songs to pick from. So it's 10,000 to the power of 10 possible sequences. That's not tracked. You can't just explore it. You can't just enumerate it and hope you stumble across something good. So in reinforcement learning nomenclature, this is called solving an MDP. Now, if the problem is small enough, there's very efficient algorithms for doing this, finding the optimal solution. Fortunately, if the state action space is too large, you can't do it. So you have to use different types of approaches. And one common popular approach is called Monte Carlo tree search. It's a Monte Carlo search algorithm, which basically leverages a tree structure to explore the different sub-options intelligently. The basic idea is that as long as you have some means of reasoning abstractly without actively operating in the environment, you can counterfactually reason like, well, if I play that song and then I played another one song after it and then another one, what am I expecting to see? Sort of that kind of branch and bound type reasoning. Now, you can't use Monte Carlo tree search for this problem off the cuff either, because the search space is too large. If you think about just exploring a tree, and the branching factor is how many actions you have. If you have 10,000 songs, that's 10,000 branches. So just exploring that tree, even for like a depth of 3 or 4 songs, the tree is going to be too large and you're not going to explore efficiently. And the second thing is, because the branching factor is too high, you're not actually, so you are both punished for just the size of the number of possible trajectories, and both by the fact that for a given next trajectory, you have too many options to consider. So you have to use a more sophisticated variant that doesn't necessarily aim for optimal, but tries to retain good trajectories and not let them get lost in the numbers game that is aggregating different rollouts. And the second thing that you can do is not just reason over songs directly, but introduce some kind of intermediate abstraction. This is the technical slide of this. It's the paper I published at ICML. I'm going to skip it. I'm just going to talk about the high-level idea, which is basically the idea is that instead of just reasoning abstractly over songs, you introduce some kind of abstract song representation, and then you alternate. You think, I want to try out a song of type X, and then out of the type, you try out different songs. And this is all done in simulation. So this is how you're mitigating the branching factor issue. And the second thing is that you have a tunable coefficient, which basically tells you how much you're willing to sacrifice optimality in favor of retaining good enough performance. And you can see that in the vanilla case where you're just trying to maximize listener enjoyment, setting that coefficient to 0.5 does better than the standard algorithm that without any kind of sophisticated search algorithms. And if you're trying to do something more complicated, which makes it even harder to find good trajectories, like you want to reward extra for novelty, like you want to play something that people haven't heard, which makes it harder because if he hasn't heard it, then it becomes less likely that you would actually know what they like. Then using that kind of reasoning becomes critical, because without that, the learning algorithm doesn't do very well at all. So, and I want to just point out before I continue onwards that this isn't this work is novel in the sense that it was the first to consider reinforcement learning in music playlist recommendation and try to actively model sequence preferences in online fashion. This is all not using, if you consider the vanilla music recommendation type, it's based typically like collaborative filtering, and it's typically you feed it it's like the Netflix challenge. You feed it like millions of users and millions of songs, and you let it crunch on a cluster for like 2 weeks, and then you come up with a model. Nobody understands that model, but you play it to the people anyways, and if some people complain, it doesn't matter because you're making tons of money from ad revenue. But in this case, we wanted to do something that you could actually learn on the fly from interaction on a laptop like this one. But people reasoning about playlist prediction is an existing body of work, and you could mention something like Chen et al.'s paper from 2012. Eisenberg was working on basically building autonomous radio channels, essentially. And a similar work from Gilles et al., McPhee and Lancret, who basically, that's an interesting work actually, where they try to use tools from natural language processing to try and predict n-grams of songs. And I also want to point out that all this stuff I mentioned, when you do it online, it's fine if you're doing it for a session of an hour, but if you now want to keep track of what people like over the period of months, then everything's going to change on you. So you have to actually reason about how people's preferences evolve over time. And it actually reduces to one of the most pervasive of machine learning problems in general, which is concept drift. And we had an interesting paper on that, actually using reinforcement learning tools for concept drift in lifelong autonomous learning. It was published at AMOS last year. And to tie all this together, I want to recap and just say that, first of all, in case it wasn't obvious, sequence does matter. Now, it may not matter to everyone, but it matters to a lot of people. And it's possible to learn preferences over sequence, even in a short, some preferences, even in a relatively short session of 10 to 25 songs. And that doing so, using a reinforcement learning approach, leads to better music recommendation than a baseline that ignores transitions completely. And you can do this with relatively modest computational means, without any powerful priors, and without like tons of pre-existing data. Okay, so I'm gonna change gears after this. So if you have any questions about this, it's a good time to stop and ask them. How much? How 10 grand? Okay, perfect. Yeah. Questions? Yes.
Okay, so I'm just curious when you're talking about trying to is that people enjoy sequencing, but when we listen to music, depending on what we do, that has a lot to do on how we want to process the music. It's different if I'm sponsoring a dinner and I have a guest, and then I want to listen to one type of music, whereas if I'm driving to the game and I'm getting ready to watch the game, I'm going to want to see. So what does that factor in?
I mean, the session is local. So in this, at least in this context, the initial, the main work that was discussing, it basically, I want to say that it wouldn't necessarily start entirely afresh, but it starts afresh at least with respect to what specific thing you're looking for that specific session. And it tries to, within 10 to 25 songs, which may not be fast enough, by the way, for a natural deployed system, but in this context of this science work, it tries to figure out within 10 to 25 songs what you're into right now. It makes, the only real assumption that it makes in that sense is that whatever it is that you want right now isn't going to change in the next hour. Because if it's going to change every other song, the system is going to have a problem. But I know, I have a 3-year-old. I know what that's like. but in that sense, and on the other hand, if you're thinking about like long-term adaptation, then definitely one of the things that people have been looking into, and it's something that I've been looking into, is the idea of conditional preferences, or like like having latent models where you say like you basically expect people to have different preferences based on their background activity, but you don't know the background activity. So part of your learning process is to try to reverse engineer based on your interaction, what's your background activity, and then adapt your model to that. Or say, there's different types of people in the world. There's people who like sports, and there's people who like lounge music, and there's people who like free jazz, and there's people who like acid house. I don't know. And it doesn't mean that you're one of them forever. It means that for a single session, you're some blend of these, and then it tries to recover the blend. So this framework can be easily augmented with that type of reasoning. But it's not the vanilla flavor of it, if that makes sense. Okay. Any other questions? Yes?
You talked about the problem of having kind of too many branches because you have too many songs in your action space. Have you considered, like, if you have the song preferences, right, there's some songs that you just like more. And since you already know that the songs are kind of...
Oh yeah, in the actual algorithm, it doesn't really plan over all songs. It plans over a subsection, a tunable subsection of the songs that we expect you to like. And honestly, I looked at like half, a quarter, 10%. Around quarter is does pretty well. If you go down that, remember your model of what you actually, my model of what you actually like is really noisy. I've only known you for like 10 songs. Imagine if I knew you in an actual party with listening to 10 songs and you just told me what you thought about those 10 songs. Imagine how biased that could be, an estimate of what kind of music you actually like. So you don't want to make too sweeping judgments about what songs to use and not use, because then you'll be throwing out a lot of good songs. But you also don't want to play stuff that you definitely do not like. So there's a game there. It cuts down, it matters empirically, but if you think about it in terms of big O notation, like complexity theory-wise, it doesn't change by order of magnitude, because you can't really trim down that much. So, but if you had a better model of what songs you actually liked, then that definitely could be leveraged. Does that make sense? Any other questions? Yes?
Does the environment include the day and the time of the day to be able to put some contextual awareness?
Can it? For sure. Have I actually done that? No. But I mean, this project was kind of like agnostic learning. The idea was that I don't know what time it is and I don't know what you are. It's going to start from scratch. It starts with a uniform prior, and it's going to try and figure out within 25 songs before it actually starts exploiting if it can figure out something about what you like. And it figures out something. It's not going to end up, after 25 songs, this is going to uncover the secret that is you. But it's going to do better than just ignoring transitions altogether. Yes?
I know this has been done in the music, but is that applicable to some of the time series, like the financial
Absolutely, and
data?
I actually looked into it in terms of like news article recommendation. And people who've read this article, you finish reading an article, what you're going to recommend your next article to read. So everything in this framework is entirely generic. It doesn't know that it's recommending music. I mean, the feature, the only place where the features, yes. So you will just need to find a way of representing it as a vector. Once it's represented as a vector, it can recommend anything that it's in sequence. Does that make sense?
Yeah, definitely. But I was thinking like in terms of stock financial data. Can you
Oh, okay.
can it be-
The vector would probably be like the slow that you look at, right?
I mean, yeah, it really depends on what you need to have a raw representation of the whole data set where you can then, for stocks, I mean, are you basically it's just trying to recommend you stocks to buy based on stocks that you've already bought or
people
something?
are buying or something?
I mean, I would be reluctant to make people lose money, but you could hypothetically. I don't see a technical reason like why you wouldn't. It's just I don't know. Basically, you'd be encouraging people to double down on whatever decision that they made, which may not be conducive to not losing all your savings. Yes.
So you said in the MCTS, instead to like decrease the feature space it searches, it looks for songs that it's like, so it's like some kind of dimensionality.
So yeah, so the basic MCTS is just a search algorithm for finding good solutions in complex dynamic spaces. Using that kind of heuristic in this domain without any adaptations is not conducive to finding good solutions. So you have to figure out a way to make search more tractable. One of the things that I've done was, instead of planning directly on songs, you say, let's group songs by shared characteristics and then plan over groups of songs and then plan over songs. So it's first picks a group, then picks a song, alternating. So what you've done is your sequence is now twice as long, but it's easier to explore. But you make these, you lose some representational power by doing this because you're missing on a lot of songs at every point where you pick a specific song type and you're grouping together songs that are not necessarily all the same thing. But you're making those simplifying assumptions just because otherwise you're dead in the water. So does that answer your question?
So kind of like patterns that people like this song, like this type of song, and then after they listen to this type of song, they want to listen to this type of song.
Kind of, I mean, you could definitely use it analytically post hoc to say like, what kind of song type transitions are more popular than others. That's interesting follow-up work that I haven't had time to go into, but it's definitely, I would be definitely happy if somebody did it and cited me. Yes?
Can you explain a bit about the reward system? So is it like if you got the right recommendation, you add it back in your...
So, oh yeah, that's actually, I mean, it's nuanced, but the idea is that, what was this? Okay, so the idea is that you get a reward signal, which is basically in this case a thumbs up or a thumbs down. Then you need to sort of reverse engineer, wait, what was conducive to this? Was it the preference, was it the transition preference, or was it the song itself? And the only thing you can go with is your actual model. So you can say, how much was I expecting to see a reward for the transition versus the reward versus the song, versus how much I got. And then you basically reassign the weights proportionately. And then it's basically gradient descent. So you just update that. You get that as a gradient. Does that make sense?
Yeah.
Okay. Any other questions on this part? Because I'm going to switch gears. Yes?
It's possible to state your model to deep learning, reinforcement learning.
Sorry?
It's possible to state your model to reinforcement deep learning.
I don't understand. Okay, so continue.
Your model,
Mhm.
it's possible to state to deep learning.
Absolutely. I mean, the model, it's already done. Just like you can plug in any reinforcement learning model of your choosing to this, basically, to learn those weights. I have found that there's not enough data in a 50-song trial with a single subject to be conducive to efficient learning with like deep learning paradigms. But if you're working with million users like Pandora or Spotify, then it's definitely doable. I had a correspondent with somebody who was trying it, so it definitely makes sense. Any other questions? Okay, awesome. So I'm going to switch to a slightly different, even though not entirely unrelated topic, which is the impact of music on human decision making and where do agents fit back into the loop. So we were talking about how the agent is trying to predict people's preferences on the fly and recommend music to it. Now imagine that you're trying to do something else with a person, be it like you're playing a game with it, or you are an autonomous car and there's people coming in front of you, and let's assume in a weird world that you actually knew what music they were listening to. Maybe their windows rolled down and they're listening to Riding Dirty, whatever it is, so it's very loud. There's an interesting question here. First of all, is like, how does music actually affect people's decision making in this context? And interestingly, not a lot of people have actually tried to build predictive models of how decision making is affected by music. Can we model it? And I'm going to get together, like, can we actually use that model for human-agent interaction? But the first attempt was to figure out whether music affects people's decision-making in a quantitatively predictable way, and can you predict that? So, and this is a series of papers that were published between 2015 and 2018. Welcome to go to my webpage, look them up. Fascinating reads all, I'm sure. Now, let's imagine an experiment where I'm going to flash you a word. Now it can be a word that's very charged, like war, or like homicide, or it can be something nice, like sunshine, or it can be something neutral, like spanner, or shelf, whatever. And all you have to do is, you need to tell me if that word is positive or negative. Is it like a happy word or a sad word? The only caveat is, the thing that makes it not be a task you would give a 3-year-old, is that you have like 2 seconds to do it. The word flashes, gut reaction. What do you think this word is? And if you don't answer within 2.5 seconds, the word's going to go away, and then the word's going to come up. So there's no reasoning, like active, conscious reasoning. Gut reaction responses to the words that you see. Now, we know that if you think about words that have semantic meaning, and then that clashes with how the word is represented, then people are having a hard time. Like if I show you the word red and it's written in green, people are slower to read it than if it's red written in red. This is called the Stroop effect in psychology. Now the question becomes, is there a Stroop effect, or the analog of a Stroop effect in music? And can you actually quantify it like with a statistical model? Can you actually model it computationally? So roughly we had basically run an experiment where people basically didn't want to just describe, and they had to classify words, and the trick was that they were listening to music in the background, and that was the control condition. And so words were flashing, and music was playing in the background. Looks like this. Okay, so what kind of model would you use for this type of binary decision making? So it turns out there is already a pretty good model for understanding the decision dynamics in psychology theory, at least. It's called the drift diffusion model. The idea is that you are gathering evidence as you interact. It is in itself, by the way, a reinforcement learning model. It's like it perceives decision making as a Markov decision process, where you're basically trying to gather evidence from the environment. In this case, it's just looking at the word really hard and trying to understand what it means. Then your brain processes it and it tries to reach a decision. There's 2 decision boundaries. Either, top, which is positive, you label the word as positive, or downwards, you label the word as negative. Where you start in this slope, in this geometric model, is your response bias. Like, without seeing any evidence, how inclined are you to say something is happy versus sad? I'm going to go into what happy and sad even means in this context in a second. And how fast it takes you to reach a decision in each direction is what's called the stimulus bias. Are you faster to process negative information versus positive information? And boundary separation is how much evidence do you need to reach a decision, secure caution. Some people need more evidence to make a decision. Some people need less time to process before they reach a decision. And there's these basic neural elements, which are the non-decision time. Just the time it takes you to encode the data, pass it to the brain, then encode it back, send the motor response to actually click the keyboard. So this model assumes that the decision is made by this geometric process, but it's done in a stochastic way. And then when you have the actual observations, you can basically fit the coefficients. And the nice thing is you take 80% of the data, fit a model, and then check the prediction on the rest of the 20s off the out of sample accuracy. And then actually, a lot of times for this type of experiments, you get we're getting like about 98% fit between the fitted coefficients and the output. So this model fits this type of decision dynamic really well. Now, first of all, even without now, I'm calling this type of music happy and sad music, but honestly, this is just like kind of aesthetic judgment. The idea is that there's type of music that we culturally agree that are happy, and there's songs that we culturally agree that are sad. And since we didn't want to be biased by my personal preferences as to what's happy and what's sad, we took another batch of hapless undergrads and had them just rate a bunch of songs that we played to, and we picked ones that were at the extremes. Also, they were all instrumental, because the one moment there's actual words, people's attention gets completely attracted to the words sung, and that would completely corrupt the experiment. So it has to be instrumental music. Also, it's all kind of scraped from the darkest bottoms of the internet. It had to be stuff that people don't know, because if you're playing Stairway to Heaven or something, in the instrumental version, people would still recognize it. So that also biases people's response to the music. Now, the first thing you can see, this is not fitted model anything, just probabilities, just likelihoods. Negative stays negative. Like whether you're listening to a sad song or a happy song, people are still, as likely to classify words as negative. When it comes to neutral words, people were more likely to classify neutral words as happy and positive words as happy when they were listening to happy music. So off the cuff, we have a statistically, an asterisk here basically signifies statistical significance. So we can establish that there is an effect, first step. Now, look at the normalized response times. People were much slower to classify words as happy when they were listening to sad music. This is the effect that you see here. This is statistically, completely separable, statistically significant bars are confidence intervals. Now, when you look at the decomposition of the fitted model, we see that the biggest difference, the only statistically significant difference, is the response bias. If you recall, it's this thing. It's how much you're primed to expect something. So what this actually means, it means that music affects people's priors when they're expecting other stimuli. If you're listening to happy music, you're expecting happy words. If you're listening to sad music, you're expecting sad words. We're more likely to expect sad words. Now, it's also interesting that you can actually correlate this with specific properties of music, like ones that I actually like, is how many major chords there are in the song. That is linearly correlated with how likely you are to classify neutral words as happy, for instance. And how, the faster, the louder the music is, the more likely you are to classify something as happy. And the faster you are to classify happy words as happy, And the same with tempo. The faster music is, the happier we tend to perceive it. Now, this is, of course, too small a subject to make sweeping arguments about like the nature of music and its impact, but it shows us that there is an effect. And this effect is, by the way, robust, because we replicated this experiment with two different sets of people where we got the same results. Now, what about different types of tests, like quantitative reasoning? I don't know if I have enough time to I mean, there's plenty of time. So, unless people want to rebel, you just get up and leave if you're I'm boring you. And I won't take offense, honestly. Let's consider a different experiment where I toss a coin, and before and I basically tell you, you get to, I'm heads, you're tails. The only thing that changes is the betting odds. Like, it's 50-50 either way. But let's say if I win, I win $2. If you win, and you lose $2. If you win, you win $10. So it's 2 to 10. Is that a bet you should take? If you win, it's 50-50. If you win, you win 10. If I win, I win 2. Is that a bet you should take? Absolutely. If it was the other way around, absolutely not. So I show people odds like this, 50-50, and they just need to decide, are they betting or folding? Now, so in that case, so for instance, like 15 to 5, that's pretty good. 5 to 15, it's pretty bad. Now, we do the same type of music. Same background music, and we just change the types of odds. I should give you really bad bets, good bets, and really good bets. It's skewed, because people are risk averse, you have to skew this so that the really bad bets are not nearly as bad as how good the good bets are, because otherwise people would just fold all the time. But the cool thing is, when you're listening to happy music versus sad music, people were much more likely to fold in the bad bets versus the good bets. So people were making better decisions when they were listening to happy music versus sad music. Now, basically you can actually model this as what we call discriminability. How much you're likely to accept good bets versus minus how much you're likely to reject bad bets. So it's basically the bigger the gap, that means that you're more likely to accept, the bigger the ratio between accepting good bets and accepting bad bets. So the discriminability factor flew through the roof. It's like 3 standard deviations higher when you're listening to happy music versus sad music. So it could be that, this is not to say that we understand the model that dominates this. It could be just like sad music really kind of annoys you and upsets you and distracts you or something, whereas happy music gets you in this zone or whatever. And it's interesting because in gambling journals, there's actually a journal for gambling studies. They published a paper in like 2000 and something that faster music made people make faster bets. But they did not do this type of analysis, and it wasn't predictive. It was just, we gathered a bunch of data, and this is what we got. And this is why it was published in like the Journal of Gambling Studies and not like Nature. So, but I'm saying that there was some evidence before coming when this has existed. Now, and again, you can actually recover specific attributes of music that help predict this type of dynamic. Now, this is all great, but it's more on the board, more like computational neuroscience, statistical learning, etc. If we want to get back agency into the game, the question becomes: can knowing something like background music or background information in general, you can hear me fine, right? If you can hear background information, you know some background information about the user, can you model how it impacts the listener in such a way that it actually helps you interact more efficiently with the person? So for that, we have a separate experiment in a very different domain, where you have two cars. One is controlled by a human, the red car, just trying to cross an intersection. The blue car is controlled by an autonomous agent, and it basically needs to decide when and how to drive relative to the human listener. The only trick is that this car may or may not know what music you're listening to as you're driving. And then it becomes a question as, does knowing what music you're listening to can lead to better person-agent cooperation? Can it lead to safer driving? Can it lead to fewer crashes or faster over ultraversal times? The answer is, well, so first of all, how do you model this? Well, you basically, now you can, for instance, we basically use, it's not exactly deep learning because the amount of data are smaller, but it is, as it interacts with the person, it basically learns a DDQN model with experience replay, and it has two variants. One has music awareness, one doesn't. And the question becomes, can you predict your actions more efficiently when you actually know what music people are listening to? And the results are very distinct. Like, if you consider, for instance, just random exploration, how long it takes you on average, the autonomous car to cross the intersection, it's this value. If you try to learn a reinforcement learning model for car traversal, you reduce your wait times substantially. And if you actually know the music, it's reduced even more dramatically. I don't want to dive too deeply into the details of this, but the core idea is that we can actually show that the biggest difference is in the sad music. So the model is aware that different types of music exist, figured out that when people listen to music, and this is also a separate study that I published, where you can actually show that people's driving behavior changes in different ways when they're listening to different types of music. And what the model recovered was that people are more hesitant and slower when they listen to sad music. And then it learns to exploit it by being more aggressive when it knows that somebody is listening to sad music. Now you can come and say, actually I don't know if I included that slide. Well, you can come and say, well, that's, so it drives faster, that it's just being reckless. But you can actually show that the likelihood of a crash also reduced, or at the very least wasn't statistically significantly different with and without music. So it was getting better performance without increased risk. Okay, so let's tie it all together. So we're using different computational statistical models to decompose behavioral data into meaningful constructs. And then we can basically show how different types of music affected different types of decision components in different tasks. And this can be modeled and predicted by a computational model. Now, we also show, this is more like on the musicology side, we can actually show that there's interesting non-trivial relationship between those different music facets and the decision making. But lastly, and most importantly for me as an AI researcher, is that an agent can actually leverage this information, this modeling, to incorporate it in its model learning to lead to more efficient interaction with a human participant. And also want to say that this work is again not in a vacuum. People have been considering the impact of music on human psychology and perception in various different facets, but it is the first to actually tie together agency and reinforcement learning and the impact of music on decision making in a predictive way. And all this type of work is, for me, part of the longer term vision, which I think is also partially shared by my company, Spark Cognition, which is to change the world with artificial intelligence and impact in a wide way different facets of human interaction and human-computer interaction and entire technologies. And I'm giving music as an example for like something off the beaten path where this affects, but at Spark Cognition, we impact different industries all the time in a very deep and pervasive way. And with that, I would like to invite you to come to Time Machine 2019. It's a conference that we're organizing. It's a mixed crowd of business and academia and technologists and people who are interested in the impact of technology and AI specifically on society and on the future. And it's got a lot of really good speakers. I attended last year. It was great. I wholeheartedly represent, if you're interested in this type of stuff, I warmly advise you to join as well. And there's a bunch of flyers out there. Please pick one, give them to your friends, bring them to your workplace, use them as fans for barbecue. Very good cardboard. No, seriously, take them, keep them to heart. It's next month, and we would be happy to see you there. And with that, I'll leave the floor to questions. Thank you so much for giving me the time to talk. I appreciate it. so much for your time. It was a blast. I hope you liked it.
All right.
The slides are going to be online, I'm expecting.
Yeah, so we'll post the slides in the meetup group, and if you have any further follow-up question,
My
you can
email
reach
is
out-
also in
Yeah, you can reach out to him.
Yes, absolutely.
There are some pizzas left if you want to grab.
To the victors, the pizza.
Yeah. All right, thanks for
Thanks a lot.
coming.
Thank you so much.
See you in
Appreciate
the
it.
next meetup.
Thank you.
I never got to say bye.
Oh my god. No, I actually moved out last month. Yeah, exactly. So, oh hi, I'm Brittany. Nice to meet you. I used to live right next door, same building. Yeah, long time. So I moved about 10 miles east to the domain. In a house over there by Samsung.
Okay, cool. No, we moved to the branch.
Okay. Yeah. I know. Yeah, a yard and so but yeah. No, I was planning on this meetup and I was looking at the speaker and I was like, wait, what's my old neighbor?
This is very funny. Like, I wouldn't have. Austin's not that small. You know, I mean, like, so
Yeah.
what do you do these days?
Well, I'm still at Fidelity.
Okay, cool.
But I have a really strong interest in startups and kind of innovation, especially with AI and machine learning. So I've been taking Udemy classes for a long time.
Cool. You're taking the home development and Charles Bull one?
Is that the A to Z? Okay.
Anything with Michael, he's fantastic.
That sounds familiar. Maybe I listened to three A to random A to Z and then whatever the topic is.
There's one that have like songs, songs that take home Michael Jackson, but with machine learning.
I would have remembered that.
Because I know because they said, oh, okay, great, that's that.
Oh, okay.